Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 12 for the course of control system. My name is Engineer Jaffar Ali and I am instructor for this course. In the last class we have discussed about the stability analysis, and by stability I mean to check that if the poles are on the right hand side or on the left hand side. And you know that if the poles are on the right hand side of the given plane, so the system is said to be unstable. So how do you check the stability of a system? In the last lecture we have started our discussion with the RH criteria, Hertz stability criteria, and in today's class we will be discussing some of the examples, practical numerical examples, that how you can check either the system is stable or unstable based upon their values. So let's start with a small recap. You see that this Sn is the maximum power of the characteristic equation, and this n is basically the number of degrees, or you can say the maximum power. Similarly, this an is the value associated with that, and the coefficient associated with that, this s power n, and this is the small table by which you can understand that how this Sn basically is descending till s power 0. So let's say if the value is s, we will discuss that in the next slide example inshallah. So stay with me. And this an is basically this the value associated with this thing, and similarly this an minus 2 is basically the value associated with the third term, actually not the second, not actually the third term, and this an minus 1 is the one coefficient that is associated with the this Sn minus 1. So let's start the numerical portion. But the summary of this RH criteria, that is Hurwitz criteria, is basically the number of roots in the open in the open right half plane is equal to the number of sign changes in the right first of the first column of the route array. This is the route array. You can see that this green line, this green box, is actually showing the route array, and the number of sign changes is actually depicting the value of the poles that are on the right. So let's start with the first example. In this example you can see that we have given with the this equation, the characteristic equation for a given transfer function, and the first thing that we have to do is that we have to see that what is the maximum power, or what is the degree of this equation. So the degree of this equation is basically 4. You can see that the maximum power of the s value is basically this 4 value. So start from the s power 4 and go up to s power 0. You can see that there are 5 rows, basically 1 2 3 4 and 5. So the next thing is basically you have to search for the coefficients. So coefficients is basically 1 2 3 4 and 5. So the first coefficient will be the S4 will become as it is. The second coefficient will be neglected, and we will write this 3 on this side, and again neglect this one and write this 5 over here. So the first line becomes 1 3 5, and in the second line go with the remaining that you have left, that 2 and 4. So you have to write this 2 and 4, and to complete this row you can see that there is no other value, so you can just put a 0 over here. So let's see that what is the operation. So the operation is basically you have to actually multiply this thing and subtract this thing and divide by this 2. So when you multiply 2 by 3 you get value of 6, and then you subtract this 6 with 1 cross 4, and then at the end you divide it by this value 2. So you can see that this value basically becomes 6 minus 4 divided by 2, or you can say 2 by 2, or you can say 1. So you can get the value of 1 over here. Similarly, to find the value of this space or this place, you have to do this thing from this side and like this. So you have to multiply 2 by 5, it turns out to be 10, and then you have to subtract this thing 0 and 1. So 0 ones are 0, and then you have to divide it by this term. So 2, this turns out to be 5. So you got 5 over here. Now to find the value of this term, you have to do the same operation, but by using these the upper two rows, not the top row, the upper two rows of this row. So when you have to when you multiply this 4 by 1, you get 4. Then you subtract this with the minus 10, and then you divide it by the lower, that is 1. So it turns out to be minus 6. So you got minus 6 over here. Now to find the value of this space or this place, you have to use these two rows, and you can take this thing as 0. So you have to basically minus into this thing, turns out to be minus 30, and you have to subtract it with 0, and you have to divide it with this thing, actually minus 6. So it turns out to be plus 5. This minus thing will be cancelled with this minus, and 6 ones are 6 fives are, so the value will be 5. So you got this thing. So this will be your route array table, route array. This is basically your array. Let me clear it for you. You can see that there is two sign change actually in this route array. You can see that there are two steps where the sign and change. The sign is basically positive over here, the positive over here, it is also positive over here, but there is a sign change over here, and there is slight of another sign change, minus 2 again, plus. So there are two sign changes. It means there are two poles that are on the right half plane. So the system is said to be unstable, because you know that if any of even one pole is on the right half plane, the signal is the system is unstable. But in this case, there are two poles that are on the right hand side. So you can see that this system is basically unstable. Let's talk about this another example. We have to find the value of this. We have given with the transfer function. So you can see that we are given with the block diagram, and this is the R as the input and CS is the output. So this is your characteristic equation in which the maximum power is S power 3. So this S3 starts from here, and S2, then S1, that's an S power 0. The coefficient of S3 was 1, and with by skipping this term, we have going to it towards this. So 1, 31 and 0, because there is no term on this side. So 1, 31 and 0, and the remaining coefficients will be on the second row, that is 10 and 1030. So this 10 and 1030 are over here. So now if you do the same operation that we have discussed, the value turned out to be 72 over here and 103 over here. So you can see that if you search about the route array table, this turns out to be 1, 1 minus 72 and plus 103. So you can see that again there are only two signs are changing, that is, this is from plus to minus, and this is again from minus to plus. So there are two sign changes. It means there are two poles that are on the right half plane So the system is said to be unstable. So this is basically your criteria of this RH to check the stability. Let's talk about this example. You can see that there is S3, S2, 2S plus 24. So S3, S2, S1 and S0, and the coefficients were 1, 1, 2 and 24. So 1 is by skipping this one, and 2 and skip this one, and in the second row you will be putting these things that you've just skipped in the first attempt, 124. So when you multiply this thing, you get 2, you minus it with this, the product of this thing, that is 24, and you divide it by this one. So there's nothing to worry about. Anything divided by 1 turns out to be itself. So it's come to be minus 22, and this will be 0, and this will be again, if you multiply this thing and subtract this thing with 0 and divide by 24, you will again get this 24. So this is your table, and this is your route array. This is 1, 1, minus 24 and plus minus 22 and plus 24. So we can see that there are the sign changes from plus 1 to minus 22, and from minus 22 it comes to plus 24. So there are two sign changes in the first column. So you can see that it means their system is unstable because there are two roots or two poles on the right half plane. You see there are two roots that are basically on the right half plane of the S plane. So the system is said to be unstable. Let's talk about another example in which you have to find the value of k for which the system is stable. So the equation of the the characteristic equation is given over here, and it has asked us up to which value of k the system will be stable. So this is a kind of interesting example. So you have to find the value of k for which the system is keeps itself as stable. So the first thing is basically you have to make the route table. So starting from S3, S2, S1 and S0, and putting the coefficients 1, then this 3, then this k. So 1, this 3, and you know that this k is a constant. Actually this k is not a variable, this is constant, so you have to skip this whole. In the second step, you basically will be placing this as this 3 and this 1 plus k. So this 3 and 1 plus k. This k is not different because these both are constants value, and these are considered as 1. So that is why we have not placed this k over here, instead of which we have placed this 1 plus k over here. So now you get this route table, and the same thing will be done again. You have to multiply this thing, then you have to subtract this from this product of this thing, and you have to divide it by 3. So when you do this operation, this 9 minus 1 becomes 8, 8 plus k divided by this 3. So 8 minus k divided by this, because this was the minus sign. So this 8 minus k divided by 3 turns out to be here. And if you do again the same thing to find this value, you will be using these two rows to find this value. You will get this 1 plus k. Now this is now up to you that how you can use this equation. This, you know that to find the value of k. So you know that in order to this system to be stable, you should be keeping k for such values that the sign should not change. So it means this thing, this 8 minus k, should be greater than 0. You have to keep this 8 minus k divided by 3 greater than 0, because if you make this thing less than 0, this will be a minus sign, and you do not want to the system to be unstable. So the minimum value for which the system will be stable is from should be greater than 0, and from this you can see that 8 minus k should be equal to should be greater than 0, and the value of k should be less than 8. From this equation you can see that if you move this minus k to this hand side, so this means that 8 is greater than k, or you can also see that should be less than 8. This means the same thing. So the value of k should be less than 8 in order to keep this value positive. Now another thing that this is basically the upper hand side. Now we have to find the lower range, the lower hand side of this k. So for that we will be using this 1 plus k. So you see that this you have to equate this equal to 0. So from there you can see that the value of k should be equal to -1. So if you put k is equal to -1, this thing, this k is -1, so this thing will become 0. So you know that you do not want your thing to be 0, you have to make it positive. So it means that you have to put the value of k should be greater than -1. The value of k should be greater than -1. It means it should be -2, -3, or anything. No, it should be greater than -1. It means k should be equal to 0 or beyond. So the value will be from -1 to 8. But it should not be, this equal to will not be over here, because if you put this equal to over here, this thing will become 0, and you do not want such case to occur. So you have to put this, we have do not have to put this equal sign over here. So this is the value of k. The value of k for which the system is said to be stable is basically ranging from -1 and 8. It should be less than 8 and it should be greater than -1. So the values that you are left with is basically starting from -1. If you draw the number line, so the values should not be 8, should not be -1, but anywhere in between. So this is the example number 4. I hope that you have learned quite a lot. So this was the first part of the lecture. I hope that you have learned these RH criteria with examples perfectly. In the second part, we will discuss some numerical problems about the different cases that can occur in this RH table. How can you solve these different cases in the later part? I'll see you in the second part of the video. Thank you very much. Allah Hafiz.